Hi students, welcome to lecture 2, which is called Light and Telescopes. In this lecture, we're going to begin to talk about some of the basic concepts that we will need to understand astronomy. The first thing I want to mention is waves. I want to talk about the basic properties of waves, and then I want to explain how light is a wave, and light is also equivalent to what we call electromagnetic radiation, which is just a fancy term for light. I'll talk a little bit about why we use that term. That will lead us into the topic of the electromagnetic spectrum. And then I would like to talk about how light is emitted and absorbed by materials. Materials meaning atoms and molecules. This will lead us to the topic of blackbody radiation and also the physics of atoms. Finally, we will get to the topic of spectroscopy, and then we will talk a little bit about optics and telescopes, hence the name of the lecture, Light and Telescopes. We will discuss the two basic laws of optics, reflection and refraction, and finally we will learn how these are applied to engineer devices which allow us to see the universe. We call these devices telescopes. Let's first start with the concept of a wave. Waves are very important in astronomy because it turns out that light, as we will see, is a wave. And of course, we see the universe as we see everything else in terms of light. So we need to understand the basic properties of waves in order to even begin to talk about astronomy observations. Let's first define what a wave is. You can think of a wave as an oscillation that contains energy. For example, suppose that you throw a pebble or a rock into a pond. That rock had energy when you threw it into the pond. It was moving, it had what we call kinetic energy, the energy of motion. And when it struck the water, it imparted some energy to the molecules that make up the pond, the water molecules. This energy is then carried over the surface of the pond in ripples or waves. So you can think of a wave as a bunch of or packet of energy that oscillates up and down. In the case of a pond, it's not so useful to talk about a packet of energy, but very soon we're going to transition to light. And in that case, we're going to start to talk about packets of energy for reasons I'll discuss later. A wave has certain properties. All waves have certain properties. I want to go through what those properties are in detail, and then we will transition to light. I should just mention that the third bullet point here in my slides mentions that a wave that consists of oscillating electromagnetic energy is called a photon, which is also a particle of light. I just wanted to briefly mention that that's coming attractions for what we'll discuss later. Let's move on to the very fundamental properties of waves that all waves have. This is how you can conceptualize a wave. A wave is an oscillation that contains energy, so that means that it goes up and it comes down. All waves therefore have crests, which are the high points, and also troughs, which are the low points. So this is a crest, for example. All these are crests, and then these are troughs. The middle of the wave is referred to as, if I can draw a line, straight line, is referred to as the undisturbed state. That's the middle of the wave in between the crests and the troughs. In this case, the word disturbed refers to, you can think of it for now as a medium that's disturbed. For example, a pond. If you disturb a pond, that means you throw a rock into it or a bird lands on it or something, and then the molecules will oscillate up and down. So that's what we mean when we say a disturbance. So in this case, the undisturbed state refers to the state with no wave, basically. The amplitude of a wave is the distance between the undisturbed state and the crest. In other words, it's the height of the wave, but it's measured from the middle of the wave, not from the bottom, not from the trough. The amplitude is here in the diagram. Waves also have wavelengths. The wavelength is the distance between one crest and a subsequent crest or one trough and a subsequent trough. Or actually, it's a distance between one point on a wave and the subsequent corresponding point on the wave. So let me try to draw this for you, since I think that's easier than saying it. Okay, so this is one wavelength. The distance between these two vertical lines, this is the wavelength. The symbol we use for wavelength, by the way, is what we call lambda. This is a Greek letter, and you write it like this. This is the symbol for wavelength, and we will use this symbol instead of writing the word wavelength because it's much easier than writing the word. And the point I was making before is that the wavelength is the distance between one crest and the subsequent crest, the next one, or, this is the same thing, the distance between one trough and the subsequent trough. These two distances are the same. Or you can pick any point on the wave. It doesn't have to be a crest or a trough. Let's say this point here, and then you just have to pick the corresponding point. If I could draw, this would be much easier. You just have to pick the corresponding point in the next oscillation. So this red circle that I just drew represents one specific point. I just picked it out of the air. That corresponds to this part of the wave where the wave is moving up to the crest, let's say. And if I pick the same point in the next oscillation of the wave, I can then define the wavelength as a distance between them. So all of these are exactly the same. Let's talk about the frequency. The frequency is the number of oscillations per second. If I were to stare at the wave, let's say in one particular direction, so I were to stare at, let's say, this point, choosing a random point, I could then measure the number of oscillations, the number of up and down phases, if you like, that the wave goes through per second. If you stare at this point, right, let's say this is you, you're going to notice the wave moving up and down, up and down. And one complete oscillation is going to correspond to one wavelength. That's what I just defined earlier. And the number of oscillations per second is the frequency. How is the frequency related to the wavelength? Well, if I take the number of oscillations per second and I multiply by the frequency, if I take the number of oscillations per second, which is the frequency, and I multiply by the wavelength, that will give me the speed of the wave. Which makes sense because if a wave is moving up and down very quickly, you would think it's moving fast. But if that wave has a really tiny wavelength, then it's not moving as fast as you might think because the wave is sort of scrunched up. So if a wave has a very large frequency and a very large wavelength, it must be moving very quickly. And this, therefore, is the relationship between the wavelength and the frequency. Lambda times f equals v, which is the speed of the wave. There's another important concept which we're going to be employing not just for waves, but also for orbiting planets and stars, for example, which is that of the period. The period is the time required to complete one oscillation. So it's sort of the opposite of the frequency. The opposite of the frequency. In this context, the word opposite is not very precise. We should say reciprocal. But it's the opposite concept. So instead of the number of oscillations per second, it's the time required to complete one oscillation. Therefore, in order to find the period, which is symbolized with a t, by the way, I forgot to say the frequency is symbolized by an f here. In order to find the period, we simply take the reciprocal of the frequency, 1 over the frequency. These are the basic properties of waves that you all should know. And now what we want to do is apply these to the particular kind of waves that we're going to be interested in, to the exclusion of basically everything else, and that is the light wave. All of these things apply directly to a wave of light. But there's one little caveat, and that is that the speed of light is a constant. This is a universal constant. I should say the speed of light in vacuum. We will talk a little bit later about how light can move in different speeds in different media, like in water or diamond, etc. But in a vacuum through space, light has a constant speed. This is true even if you're going toward the light wave or away from the light wave. So if you're in space and you have a flashlight, let's say you're moving in a rocket ship very quickly in whatever direction, and you shine light in your direction of motion, you might think that you're catching up to the light wave a little bit if you move really quickly. But actually the light is moving away from you at exactly the same speed as if you weren't moving at all. And that speed is symbolized with a c. So the speed of light is c. And since the speed of a wave is lambda times f, c equals lambda times f. This is a very important equation that we will be employing, not necessarily to solve quantitative problems, but we'll be employing it conceptually. Let's move on then to discuss some of the properties of light in particular beyond the speed, which I just mentioned. Light is also called electromagnetic radiation. This is the first thing I want to mention. And it's useful, I think, to talk about where the word electromagnetic comes from. We don't really have time in this course, or really the need, to talk about the physics of light in great detail, but suffice it to say that a light wave actually consists of two different waves that are bundled together. One is an electric wave, the other is a magnetic wave. These waves actually correspond to the electric force and the magnetic force. You may have learned about the electric force in some physics or physical science course. This is the force that will hold a negative charge to a positive charge, or will cause a negative charge to repel a negative charge, or positive to repel positive. And the magnetic force is responsible for magnets sticking to refrigerators, for example. And it turns out, for reasons that we don't have time to discuss, that light actually consists of electric and magnetic fields, that are oscillating up and down. And you have an electric and magnetic oscillation in each light wave. So that's why we refer to light as electromagnetic radiation. The radiation part just means that light consists of energy that moves from one point to another. That's basically radiation. Radiation comes in many forms. Light is one particular kind of radiation. And I just want to emphasize here that when people refer to light in everyday conversation, they're actually really referring to only visible light, because that's the light we can see. But actually, there's many different types of light, most of which we can't see, but they're all fundamentally the same. It's all electromagnetic radiation. I'll come back to this point a little bit later. It turns out that in addition to all the stuff I've just mentioned, electromagnetic radiation, light, in other words, is a wave, but it's also a particle. This is a somewhat confusing topic that we will discuss a little bit later on in the course. But for now, I just want to tell you about it, and then we'll move on. And so the particle of light is called the photon. That's how we refer to it. And you should think of the photon as being a particle of light, but also having wave-like properties. So therefore, light is a wave and a particle. I mentioned that the speed of light is constant for all observers, and also this applies to light of any energy or of any kind. And so it's true for visible light, it's true for other kinds. Let's talk about the different kinds of light, since I've actually mentioned this a couple times without really defining what the different kinds of light are. The different kinds of light are defined based on their frequencies or their wavelengths. Frequency and wavelength are connected by this equation that I just mentioned to you. Lambda times f equals c. Remember that c is a constant for all observers. This is the speed of light in a vacuum. So if we have a wave of light which has a very large wavelength, therefore we have a very large lambda being multiplied by some number which represents the frequency equaling a constant. As lambda increases, so it's a larger and larger number, f must decrease. If I have two numbers I multiply together, let's say 2 and 3, 2 times 3 equals 6. And if the product of those two numbers is a constant, let's say 6 is a constant, then as I increase the first number, I have to decrease the second number. So for example, I can bring 2 to 4. So instead of 2 times 3 equals 6, or I'll write this out. So let's say I have 2 times 3 equals 6, right? If I increase 2 so that it's equal to 4, let's say that corresponds to the wavelength, then what happens to the second number? Clearly it has to decrease. If I keep it at 3, this is incorrect. 4 times 3 is not 6. So I have to multiply it by 3 halves. So 4 times 3 halves is 6. Okay, the point I'm trying to make is that if I increase lambda, I have to decrease f, the frequency. That's just the laws of algebra, basically. So a large lambda corresponds to a small frequency. This is a basic concept that we really need to understand, otherwise the electromagnetic spectrum will be totally opaque to us. And it's sort of a pun, right? Because we use light to see. So it will not be understandable unless we comprehend that a large wavelength equals a small frequency, and a small wavelength therefore corresponds to a large frequency. Let's talk about what a small frequency or a large frequency or wavelength actually means for light. The difference between different types of light is really that the different types of light have different energies. That's it. Otherwise, they're identical. So some light has a really large frequency, and those kinds of light, or that part of the electromagnetic spectrum, consists of light that has a lot of energy. So a large frequency means a lot of energy. I think this is intuitive because if you see a wave that's bouncing up and down really, really quickly, you would think it has more energy than a wave that's bouncing up and down very slowly. And that is indeed the case. So light that has a very high frequency, many oscillations per second, has more energy than light that has a lower frequency. Let's talk about the electromagnetic spectrum now that I've given you this basic framework for how to understand light. Here is a diagram of what we call the electromagnetic spectrum, which is really just a representation of all the different kinds of light that we have. Let's start with very low energy. All the way on this end of the spectrum, we have low energy, which means low frequency light. Remember, low frequency means low energy. High frequency means high energy. Radio waves are electromagnetic radiation. They're light that has a low frequency, or frequencies, and therefore low energies. Notice that I have two, this might be a little bit hard to see, but there are two arrows here. The frequency is increasing as I go from left to right, but the wavelength is increasing as I go from right to left. This is not surprising because remember I said a large frequency means a small wavelength and vice versa. So radio waves have very large wavelengths and very small frequencies, which means they have very low energies. As we move to the right, we get to light that has more and more energy. Infrared radiation has less energy than visible light, but more than radio. Then we get to the visible part of the spectrum, which is actually a very narrow band. And the reason we call this visible is because this is a light we can see. There's nothing else that's special about this light. It's not fundamentally different than other kinds of light. It just happens to be the light we can see. Then as we move past the visible part of the spectrum, we get to ultraviolet light. Remember, we're moving toward the part of the parts of the spectrum that have more and more energy here. Or energies rather. So ultraviolet light has more energy than visible, which is why it can be dangerous, can cause skin cancer. Then we move to X-rays, which are very dangerous. That's why when you go to the dentist and you get an X-ray of your teeth, they give you hopefully a lead apron. And they should probably give you a lead apron also, not just for your chest and your abdomen, but also for your neck. I forget what they call it, but anyway, you should ask for this because you don't want to be exposed to X-ray radiation to the extent you can help it. And then finally, we get to gamma rays, which are exceptionally dangerous. And you do not want to go to the dentist to get a gamma ray. This would kill you. So I don't know why I'm laughing here. One of the themes in this course is going to be ways to die. The universe is actually very dangerous. We live on a very excellent planet that has just the right temperature and pressure and has oxygen, and we're protected from radiation, etc. But we will talk about how in virtually every other part of the universe, as far as we can see, that's not the case. So anyway, this is one way that you could die, get exposed to gamma rays. Let's move on to this nice diagram, which is exactly the same thing. This is also depicting the electromagnetic spectrum, but it gives you at the bottom here a nice sense of what the wavelengths of the different parts of the spectrum actually correspond to. On the left side, again, we have radio waves, and you can see representations of the light down here. Notice that the frequency increases from left to right, same as before. Radio waves have wavelengths that are roughly the size of mountains, skyscrapers, maybe humans. As we get to the infrared, we have wavelengths that are roughly the size of a pinhead. And then as we move to gamma rays, we have wavelengths that are the size of atomic nuclei. I should also point out that red light has less energy than blue light. You may have learned this in a previous course, but I just want to emphasize that here. This actually becomes quite annoying because for some reason most people interpret red as being hotter than blue. For example, when you go to a hotel and you look at the faucet in the tub, you will see usually hot is red, blue is cold. This is completely backwards. Blue light has more energy than red light. This is not a convention. This is the way that light works. This is important for astronomy because we will learn that different stars tend to emit in different parts of the electromagnetic spectrum. Some stars look blue, they emit toward the blue end. Some stars look red, they emit toward the red end. Stars that look blue are hotter than stars that look red because blue light has more energy than red light. So this really is totally backwards. And next time you go to a hotel, you should complain and have them switch it for you because blue is hot and red is cold. Anyway, that's it for light for now. I want to move on to how light is emitted and absorbed by materials. This picture here looks rather weird, but the point of this slide is to emphasize the concept of what we call black body radiation. A black body is an object that absorbs all the radiation that's incident upon it and then emits that out into space. The whole point of defining a black body is that there are many objects in the world and the universe that approximate a black body. They're very close to being perfect black bodies. So this is a kind of model that we can use to understand stars, for example. Stars are very good black bodies. And because we have a model, a physical model for how radiation is absorbed and emitted by stars, we can then write down some equations which will predict what radiation we observe from the sun. So if you stare at the sun and you collect the sun's light, then you can compare that to your model for black body radiation. We're going to get back to this in just a little bit, but I just want to introduce this topic just to start off with. And then I want to talk about the actual data that we get from the sun, or not in great detail, but the overall nature of the black body radiation we get from the sun. Before I get to that, I want to talk about particles and waves a little bit. I mentioned that we would discuss a little bit more in this course the strange relationship between particles and waves. I mentioned to you that light is a particle but also a wave, and it turns out that this is generally true for all particles as far as we know. This is referred to as what we call wave-particle duality. So that just means that waves and particles are somehow connected in a weird way. Let's start by talking about a very famous experiment which discovered the electron, or allowed J.J. Thomson, rather, to discover the electron. I don't really want to go through this in any detail, but I just want to mention to you that we sometimes take for granted that the universe is composed of particles. And you might think, well, how do you determine that electrons exist or protons exist? You can't just reach into your pocket and pull out an electron and say, aha, I have an electron. You have to perform experiments which show conclusively that these particles exist. So J.J. Thomson in 1897 created an experiment, which I'm not going to go through with you in detail for lack of time. We could do a whole lecture on this. It's very interesting. But basically, he used electric and magnetic fields to produce what we call cathode rays. Cathode rays are sort of luminescent, rays, I guess you could say. The word ray here is a little bit ambiguous, as it's unclear exactly what it means, but it's like a luminescent entity that you can create using electric and magnetic fields, and it's depicted here in this picture. And there was a debate in the 19th century, in the 1800s, about whether these rays were particles or waves. And J.J. Thomson found that they behaved as if they had a charge to mass ratio. Charge to mass ratio, that's what I'm trying to say. And so therefore he discovered the electron, because particles have charge to mass ratios. So he determined that they consist of individual particles that today we call electrons. Okay. As amazing as this may seem, it turns out that subsequent experiments determined that electrons, although they are particles, also are waves. So just like light, which is a wave, has particle-like properties, an electron, which is a particle, has wave-like properties. This is the wave-particle duality I referred to earlier. I want to mention to you one key aspect of waves that we haven't, we haven't talked about. That's very important if we are to understand the basic idea of wave-particle duality. When waves interfere, or let me actually step back. If you were to emit waves toward a barrier with two openings, two slits, those waves would interfere with each other, with themselves, and they would produce what's called an interference pattern. This is unlike particles. If you were to take a bunch of particles and throw them at a wall with two holes in it, right? So this is a wall here, but there are two holes in the wall. If you were to take particles and throw them toward this wall, some of them would just bounce off the wall, right? But occasionally a particle would actually go through the wall, and then it would just hit the wall on the other side that's opposite to the hole. So imagine throwing marbles at a wall with two holes in it, and then there's a wall on the other side. Those marbles are just going to go through, if I can draw arrows here, go through the holes and then just hit the wall on the other side, as particles do. But if electrons are waves, and they are in at least a certain sense, then instead of those particles individually going through the holes and striking the other side, because they have wave-like properties, they will interact with each other and create an interference pattern. And this diagram here is supposed to be an animation. And I'm going to, it doesn't work in this mode, but I'm going to try to force it to work. Okay, so here's what we actually see. I hope you can see this. So this is an interference pattern. These waves are going through the slits. They're interfering with themselves, and then they produce this pattern, this light and dark pattern. So what does this actually look like? Well, I have the result of an experiment. Okay, the result of an experiment that is of exactly the same form that I was just talking about. Imagine you take electrons, these particles, and so again, go back to this experiment here, and you emit electrons, you throw them at a barrier that has two slits in it, and then on the other side you have another wall, a far wall, and that far wall has some film, which will then tell you where each electron hits the film. So what you would expect to find is electrons would just hit the parts of the film that are opposite to the slits. In reality, even if you emit one electron at a time, what you find is an interference pattern. So you find that electrons behave like waves. This is what you find over time. This is an interference pattern. We have a light fringe, that's what we call it, a fringe, a light band, part of the film. Another one here, and then in between the light parts, we have dark parts. This is a dark part here, here, and here. So that's what we mean when we refer to an interference pattern. The point of these slides is just to emphasize here that experiments have determined that things we think of as just being waves, like light, have particle-like properties. Actually, that part we're going to get to in the next slide. We haven't quite done that yet, but that is true. And then also things we think of as just being particles, like electrons, have wave-like properties. Let's move on to blackbody radiation, as I promised. There are two goals here that I have in discussing blackbody radiation. One is to just teach you the basic mechanics of how stars emit light. I'm not talking about like the particle physics. I'm just talking about what kind of light would be emitted by a star. How would you know what kind of light the sun would tend to emit? What is that related to? That's one goal. The other goal is to use this as an example of how light is a particle and a wave at the same time. Remember, blackbody radiation is the radiation emitted by a black body, and there are many objects which approximate black bodies in the universe. These are basically stars. Stars and planets approximate black bodies. If you were to observe, that's what I meant to say, the light that's emitted by the sun as a function of the wavelength, what you would find is this curve here. So this represents the intensity of the light, basically the amount of light that is emitted as a function of wavelength. In other words, how much light in the X-ray part of the spectrum does the sun emit versus how much light in the radio wave part of the spectrum? Does the sun tend to emit more radio waves or X-rays or gamma rays or visible light or what? So this you could refer to as the intensity of the light, roughly. And the answer, it turns out, is that the sun emits very, very few low wavelength, small wavelength particles of light. This is wavelength here, lambda. So this is small wavelength, this is wavelength close to 0, and this is wavelength very, very large on the right side. So the sun emits very few small wavelength particles of light. In other words, small wavelength, of course, corresponds to gamma rays, X-rays, so very few of those. The intensity increases to a peak as the wavelength gets to visible light, and then, this is for the sun, and then it decreases here, basically exponentially, as the wavelength continues to increase so that the sun emits very few radio waves, for example. This is what we actually observe when we look at the light emitted by the sun. This brings up an interesting point, however, because this is not what people thought they would see in the 19th century. In the 19th century, people had the conception that light was just a wave. And it turns out that if you apply the physics that corresponds to that idea, that light is just a wave, you end up predicting that the intensity of light that would be emitted by the sun would be proportional to 1 over lambda to the 4th. So in other words, in the 19th century, people predicted from the physics they understood at the time that as the wavelength of light decreases, I'm talking about the wavelengths of light emitted by the sun, for example, the intensity of that light emitted by the sun would increase by a factor of 4. So what does this mean? This means 1 over 2 is larger than 1 over 3, right? 1/3 is smaller than 1/2. So as lambda increases, the 19th century physics that people thought was true at the time predicted that the intensity of light would go to infinity. As lambda equals 0, let's see if I can write this out. Okay, thanks for your patience while I get the right pen. So as lambda goes to 0, 1 over lambda to the 4th goes to infinity, because 1 divided by 0 is infinity, as people say. Or it's a little bit more precisely, it's unbounded, which means it's not really a number. So this is referred to as the ultraviolet catastrophe. That's why there's a little arrow here pointing from the right part of the curve, the upper right part of the curve. And this here, the Rayleigh-Jeans law, was or is the prediction for the radiation emitted by a black body that comes from 19th century physics, basically by assuming that light is just a wave. And as you know now, this idea is incorrect. A light is also a particle. This problem was solved by a very famous physicist that you should all know named Max Planck, who solved this problem by predicting that light is emitted in discrete packets called photons. I think the best way to describe this is that what he said is that light is sort of like currency. You can pay $1.05 for a candy bar or $1.06. You cannot pay $1.05. There's no fraction of a penny. You either have $1.05 or $1.06, nothing in between. And light is like that. Light is emitted in packets. In currency language, these would be denominations. And these packets are called photons. And you either have a particle of light emitted that has a certain energy, or you don't. There's nothing in between. Let's move on now to the application of these concepts to stars and planets, etc., because ultimately we're interested in astronomy, right? We're not studying pure physics here. So we just want to apply these concepts to the black body curves, as we call them, which is the curve I was just showing you, to different objects. Let's ask the following question. This peak that I talked about earlier, where does it come from? Or how is it? That's a very deep question, but let's ask another question, which is, what is it related to? In other words, why does the peak of the sun's black body curve correspond to visible light? And it turns out the answer to that question is because the surface temperature of the sun is around the right wavelength around, the surface temperature of the sun is around the right temperature for visible light. The temperature of the surface of the sun is around 6,000 degrees Kelvin. And this happens to correspond to visible light. And this is basically why we see visible light, because that is the light that's emitted most copiously, most numerously by the sun. If you were to take the surface of the sun and increase its temperature, then you would shift the black body radiation peak toward higher frequency parts of the spectrum. In other words, if the temperature of the surface of the sun increased, the sun would begin to emit light that has larger and larger energies. I think this is intuitive. The sun gets really hot, it emits really energetic light. If the sun were to cool down, the light it emits would be of smaller and smaller energies. Notice that in this diagram, frequency is increasing from left to right, and wavelength is decreasing from left to right. So in this diagram here, objects that have larger temperatures will have Planck radiation peaks that are to the right. I'm just going to draw all the peaks here. Let's start at the top. It's a little hard to read. Okay, I'm not even sure if it says what this is. This is just some dust cloud in space, I think. It doesn't matter what it is, but this is some astronomical object with a relatively low temperature. So notice that the Planck radiation peak is to the left of the visible spectrum, which is the vertical line that has the red and orange and blue. And then as we look at objects with larger and larger temperatures, so as we go from 60 Kelvin to 600 Kelvin, we see that the peak moves to the right toward higher frequencies. Then this is the sun. So we see that the peak corresponds to the visible part of the spectrum, roughly. And then as we get to a very hot object, 60,000 Kelvin, let's say, the Planck radiation peak is well to the right of visible light. So this object is going to emit largely in, well, it's not, I can't quite read it here, but largely probably in the ultraviolet or X-ray or whatever the peak corresponds to. Okay, so this is one of the basic things I want you to be able to do. I want you to be able to look at a Planck radiation peak, or let's say two of them, and compare and tell me which one has a higher temperature. Let's move on now to a discussion of temperature. I think that we all have an intuitive understanding of temperature. But what I would like to do is try to make this concept a little bit more precise and also talk about the different units that we have for temperature. You may be familiar with the Fahrenheit unit. I'm sure you are. When people say that it's 60 degrees outside, what they mean is 60 degrees Fahrenheit. But actually, the most common unit of temperature that we have in the world is Celsius. That's what's used pretty much everywhere else. I want to make sure that you have some intuitive understanding of what Celsius is. You probably learned that 0 Celsius is the freezing point of water at standard pressure. Or probably you just learned freezing point, but anyway, that's fine. That corresponds to 32 degrees Fahrenheit, which is 0 Celsius. The boiling point of water, again at standard pressure, is 100 degrees Celsius by definition, and that corresponds to 212 degrees Fahrenheit. The Fahrenheit scale is a bit weird because you have to remember these odd numbers. And now I want to explain to you what different Celsius and Fahrenheit measurements mean intuitively. A very cold, bloody cold day, let's say in New York City, would be maybe around the teens, as people say, meaning maybe 14, 15, 18, 12 degrees Fahrenheit. This would correspond to about minus 10 Celsius. That's a very cold winter day in New York. Room temperature is around 60, 70 degrees. That would correspond to about 18 or so Celsius. A very hot summer day might be 95 Fahrenheit. That's around 35 degrees Celsius. And then, of course, you have freezing and boiling. The most commonly used temperature measurement in astronomy is actually the Kelvin. The Kelvin unit is exactly the same as the Celsius unit, except moved toward the higher end of the range by about 273 degrees. And the reason is because 0 degrees Kelvin is defined to be the lowest possible temperature, in principle at least, that anything can have. This diagram here actually nicely encapsulates all three temperature measurements, Fahrenheit, Celsius, Kelvin. The lowest temperature anything can have is what we call absolute zero. It's actually helpful here to describe what temperature means intuitively. I think that we all have some kind of intuitive conception of temperature, but maybe we'll make it a bit more specific. Temperature is basically a measure of the average movement, the vibration, or the movement in general of molecules. If you were to zoom into a glass of water, for example, you would see that the water molecules are vibrating around. They're moving and they're vibrating. If you increase the temperature of that water, that means that you're adding energy into the molecules, which means they vibrate and move faster and faster. Eventually, if you keep doing this, a lot of the water molecules will have enough energy to escape the liquid and become gas, and that's known as boiling. If you were to decrease the temperature of water or anything else, the thermal motion, so to speak, the vibrations of the molecules would be reduced. Eventually, you would get to the point where all thermal motion essentially has ceased, and that is absolute zero. And therefore, you cannot cool anything below absolute zero. In fact, you really can't cool anything to precisely absolute zero for reasons that come from quantum mechanics, but that's a little bit beyond the scope of our discussion here. In any case, Kelvin is defined so that 0 Kelvin is absolute zero. And it turns out that absolute zero corresponds to minus 273 Celsius. Therefore, if I convert Celsius to Kelvin, I'm going to add 273 degrees. So let's go through this. Minus 273 degrees Celsius is 0 Kelvin. So I add 273 to minus 273 and I get 0. If it's a cold day, but not exceptionally cold, it might be 0 degrees Celsius. That's about 32 Fahrenheit. To convert that to Kelvin, we add 273. So during the winter, you can say, if you're telling your parents what the temperature is where you live, if they're somewhere else, for example, you can say, oh, it's a cold day here, it's 273 degrees. And that's a perfectly valid statement, except you should give the qualifier that it's in Kelvin, 273 Kelvin, which is a rather cold day. The boiling point of water is 373 degrees Kelvin. I should say that you might want to learn how to convert, I just taught you how to do it, but you might want to remember the conversion from room temperature to Kelvin, from Celsius room temperature to Kelvin. And it turns out that it's around 18 or 20 degrees Celsius, that's room temperature. So that's around 300 degrees Kelvin. 300 degrees is a nice, reasonably cool room. Again, in Kelvin. Let's talk about atoms and then spectroscopy. And then finally, we'll move on to, we have the Doppler effect as well. And then we'll move on to optics and telescopes. We talked a little bit about what we call wave-particle duality, which means that waves have particle-like properties and particles have wave-like properties. This is related to the physics of tiny stuff, of particles, and the name we have for this physics is quantum mechanics or quantum physics. We don't have the time or the need to go into quantum mechanics in any kind of real detail, but I do want to talk about the very basic properties of the atom. You may have learned what an atom looks like, or at least what people wanted you to think that the atom looks like in school. People probably taught you that the atom has a nucleus in the center, like this, and then an electron or more than one orbiting around the nucleus being composed of protons and neutrons, and then the electrons being negatively charged. And people probably taught you that this is sort of like a little solar system. You have the sun at the center, that's the nucleus, and then you have the electrons, the planets orbiting around. This is actually known as the Bohr model of the atom, B-O-H-R, and it comes from Niels Bohr, who in 1913 published this conception of the atom. This idea was actually very radical, because Niels Bohr actually didn't say that electrons orbit nuclei the way that planets orbit the sun. And the reason is because if I were to attach a giant rocket to the Earth, let's say in some kind of diabolical scheme to destroy the Earth, I could slowly move the Earth toward the sun. I could turn the rocket on and I can push the Earth toward the sun or push the Earth away from the sun. That could be in some kind of bad science fiction film or something like that. But you cannot do that with an electron orbiting the nucleus in an atom. You cannot push an electron slowly toward or away from the nucleus. And that's because electrons orbit nuclei in discrete orbits. This was Niels Bohr's famous idea. By discrete, what I mean is that it's not continuous. There's nothing in between the orbits. This is sort of like currency. You either have 1 penny or 2 pennies or 3 pennies. You don't have 1.5 pennies. Let's go to this picture here that I was boxing before. We have an electron here that's in the second orbit. Right? See, we have 3 orbits that are drawn in the diagram. This is in the second one. I can take this electron and I can move it into the lower orbit, the one that's on the inside, if I want. or I can push it out to the outer one, let's say. But there is nothing in between. I cannot take the electron and move it here. That's forbidden. And this is actually very different than the way that planets orbit the sun. When we talk about planets orbiting the sun, we're talking about what we call classical physics, in which the radius of the orbit can take on, in principle, can take on any value. It's a little bit like the volume knob on a radio. No one has radios anymore, but imagine a knob on a car radio or any kind of knob where you can increase the volume and decrease it continuously. But then imagine another, let's say, piece of electronics equipment where you can increase the volume in increments of 1. Let's say the volume goes from 0 to 100, but you can only increase or decrease by 1 or some integer. It doesn't have to be 1, but some factor of 1. So factor of 1 is a weird way of putting it, but 1 multiplied by some integer. So for example, you can increase the volume from 1 to 2, or 2 to 25, but you cannot increase it to 24.7. That is like the physics of atoms and little particles. And that's very different from the physics of planets and stars, where radii and energy can be continuous. I think I've gone on a little bit too long about this idea between classical physics and quantum physics. So let's just move on now to the mechanics of the atom. So we might say, okay, fine, we have some picture in our minds of how an atom is different than a solar system, but how do we put this into practice? So here's how we do it. The inner orbit has the lowest amount of energy. This is referred to as the ground state. That's actually here, right? So this electron is in the ground state. That is the smallest orbit. There's nothing below the ground state. So either the ground state or some other state. You can't get closer to the nucleus than this. When an electron is in a particular state or orbit, the technical term we use is state, but you can think of it as just an orbit. It has what we refer to as the ground, it's in the ground state, and it has what we refer to as the ground energy, or the lowest energy. So that we symbolize with E with a little 0, E sub 0. And that's the lowest energy that the electron can have. If the electron is bumped up to the next one, the next state, or radius, or orbit, however you want to think of it, then the electron is said to be in the first excited state. That state corresponds to an energy E1. These are just the symbols we use. It turns out E1 is greater than E0. So if I want to move the electron from the ground state to the first excited state, I have to give the electron energy. I can do that by shining a photon, a light particle, at the electron. The electron can absorb this energy and then move up to the first excited state. But here's the key point that we have to know. I cannot move the electron in between the ground state and the first excited state. So I either give the electron the right amount of energy to jump to the first excited state, or at least that amount of energy, or I don't. The amount of energy, the minimum amount of energy it takes to go from the ground state to the first excited state is E1 minus E0, the difference in the energies of the states. This you can refer to as the change in energy. This symbol here refers to change or difference. So suppose that this amount of energy here, change of E, is 1. I'm just making up a number. Suppose you need to add 1 unit of energy to bring the electron from the ground state to the first excited state. If I shine light on this electron that has an energy of 0.99, nothing will happen. The electron will not absorb any energy, and the photon will just move through the atom. If I shine light on the photon that has energy of 1, then the electron can absorb that light and move to the first excited state. This is a very key difference between the physics of the solar system, which we're going to get to later on in this course, and that of the atom. This is super important because this leads to what we call spectroscopy. And spectroscopy is how we categorize stars. It's the method by which we categorize stars. Let's think of the following thought experiment. So now that we know this about atoms, let's think of a box of gas. So here I have some gas particles. Let's say it's hydrogen, but it doesn't really matter what it is. And these gas particles consist of, they are actually atoms. These are atoms of, let's say, hydrogen. I mentioned to you that an electron can absorb a wavelength of light and move to an excited state. I should also mention this is the second excited state. This is how we name them. And then there's a third excited state, etc. That's how we name the states. So an electron can move up to a higher energy state. An electron can also go back down to a lower energy state. That's depicted here. If the electron is in the first excited state, it can emit a photon and move back down to a lower energy state. What is the energy that this photon is going to have? It's going to be exactly the energy difference between the first excited state and the ground state. Remember that photons of higher energies have higher frequencies, and lower energies correspond to lower frequencies. We learned that earlier. So that means that the frequency or the wavelength, however you want to write it, of this light is determined by the initial and final states of the electron. If the electron in a particular atom moves from the first excited state to the ground state, the wavelength of light that will be emitted will be very, very specific. It's not just any wavelength, it's a very specific wavelength of light that corresponds to the energy difference between those states. So now let's go back to our thought experiment. Suppose that I take this box of gas and I heat it up. This is fire, right? I heat it up in some way. The atoms gain energy and they will emit wavelengths of light. They'll emit light of different wavelengths. The question is, which wavelengths? If I categorize all these wavelengths, if I list them or I depict them in some kind of diagram, that's called the spectrum. The spectrum of an atom is a representation or list of all the different wavelengths of light that can be emitted or absorbed by the atom. Since we learned that the orbits or orbitals, however you want to put it, of the electrons in an atom are discrete, meaning the electrons are in one orbit or another, nothing in between, that means that the wavelengths of light that can be emitted or absorbed by an atom are also discrete. Let's take the example of hydrogen, which is the first one. If I were to heat hydrogen and then look at the light that's emitted by the electrons as they fall down to lower energy states, what I will find is that for most wavelengths, there'll be no emission at all. So I'll just have nothing except for individual bands of light. I might have a red light, green, blue, whatever. And the reason why these bands are here is because they correspond to energy differences between the states, for the reasons I mentioned, because those are the only wavelengths of light that can be emitted by an atom. And I can do this for any atom I like, sodium, helium, etc. These are just a few choices. So these are the spectra of these atoms. And the study of spectra is called spectroscopy. We can apply this to stars. This is the whole point, right? Since this is astronomy. So this is the spectrum of, or it's part of the spectrum of the sun. If you stare at the light that is emitted by the sun, what you will find is that the sun emits all kinds of wavelengths of light. But some of those wavelengths have been cut out. They're just black. They're not present. And those wavelengths of light correspond to wavelengths that are absorbed by whatever is in the atmosphere of the sun. Let's depict the sun here. So this is the sun. Right? This is the sun inside here. The sun is emitting light. But the sun has an atmosphere. As we will learn in subsequent lectures, there is stuff, there are atoms, I should say, more specifically, that are present in the atmosphere of the sun. As the sun emits light, that light passes through the atmosphere, just like light that gets to Earth from the sun passes through Earth's atmosphere. Same idea. So this light passes through, upwards, so to speak, through the sun's atmosphere, and then eventually enters vacuum of space, and then eventually some of it gets to Earth. And as that light passes through the atmosphere of the sun, because the sun's atmosphere consists of specific atoms, and those atoms have specific spectra, certain wavelengths get absorbed by those atoms. And those wavelengths are then cut out, so to speak. They're black lines. I'm just highlighting some of them, but there's a lot. And this representation of the light that's emitted by the sun is called the spectrum of the sun. And we can study this spectrum, and then we can figure out what's in the atmosphere of the sun. Let's go back to these spectra. By the way, these bands here are called spectral lines. This is the technical term. By studying the spectral lines for each atom, and by comparing those to the spectral lines we get from the sun, we can then figure out what atoms are in the atmosphere of the sun. And so therefore, spectra are sort of like fingerprints. An atom has a very specific spectrum. It's like a chemical fingerprint, and you can search for those fingerprints if you have enough time on your hands in the spectrum of the sun. I just want to point out some terminology here that I've neglected at this point to say. There's actually 3 different kinds of spectra. The first kind of a spectrum is called the continuous spectrum, and this is exactly what it looks like. It's just the electromagnetic spectrum. It's just a continuous emission of electromagnetic radiation. The spectrum that we actually see when we look at a star is called an absorption spectrum. This means that you have tons and tons of different kinds of light that's emitted from, let's say, the core of the star. So the sun, for example, emits all kinds of light. It's largely ultraviolet and visible, but it also emits some X-ray and radio waves. And this light then passes through the atmosphere. This is what I was saying earlier. Certain wavelengths get cut out. This gives us absorption lines. These are specific wavelengths of light that are absorbed by the specific atoms that are in the atmosphere of the sun. And this is referred to as an absorption spectrum. It looks like a continuous spectrum with certain wavelengths cut out. So this is what we see from stars. Then we have emission spectra. An emission spectrum looks like what I showed you when we talked about atoms. The idea here is that we have a cold object, like a box of gas, that is being heated, but the temperature is not tremendously high. It's not 6,000 Kelvin. Maybe it's 100 Kelvin is not very high, but maybe it's a few hundred Kelvin or something like that. And what we see with an emission spectrum is all the different kinds of light that can be emitted by that atom. Or it could be a collection of atoms, actually, or even molecules. Emission spectra is what we see from gas clouds, gas and dust clouds in the universe. These are called nebulae. A nebula is a giant gas and dust cloud. We'll get to this later on in the course when we talk about galaxies and different parts of galaxies. One more thing before we go on to the Doppler effect and then telescopes, and that is that I just want to remind you of this actually. We categorize stars by their spectra. So stars have absorption spectra. If you study the absorption spectrum of a particular star, you can figure out what is in the atmosphere of that star because the spectral lines are like chemical fingerprints. You can then compare those spectral lines to what we know are the spectral lines of atoms that we can determine in laboratories on Earth, and we can figure out that the sun has iron, for example. Then we categorize stars based on the kind of spectrum or spectra that they have. We'll get to that later on in the course. Okay, so that's just a quick capsule review. Let's move on to the Doppler effect, and then we will talk about telescopes and the laws of optics. While we're on the topic of light, we should discuss one really interesting effect that we observe light to have, or property maybe is a better way of saying it, property that light has, and that is called the Doppler effect. And this is really important when it comes especially to the expanding universe. We will get to this when we do cosmology at the end of the course. The point here is that if you're not moving with respect to a star, then you can see the star's light as it would appear to someone, let's say, on the surface of the star. If you're moving toward the star, so let's say we're in the space shuttle, that's, I guess, what this is supposed to be, the space shuttle. Let's say we're in the space shuttle and we're moving toward the sun really, really quickly. The Doppler effect says, it's a property of light, and it says that the light that you observe from the sun will look bluer than it does to someone not moving with respect to the sun. The same also happens if the star moves toward you. This is actually the same thing. Moving toward the star, the star moving toward you. The star will appear bluer than it otherwise would. If you're moving away from a star, or if that star is moving away from you, it will appear redder. And in practice, the way we apply this, what actually happens is that since the universe is expanding, stars are really moving away from us. We'll get to that. So this is referred to as the redshift. Stars and galaxies, not so much stars in our galaxy, but stars in other galaxies are redshifted with respect to us. So that means they look redder than they otherwise would appear. And if you're moving toward a star, this would be referred to as blue shift. All right, that's the Doppler effect. Let's finally get to telescopes. There are two kinds of telescopes. A telescope, by the way, is an object that we design to help us see the universe. I'm sure you are familiar with the idea of a telescope. You look through it and then you can see the moon or whatever. There are two basic kinds of telescopes. Each of these uses or takes advantage of a law of optics, a law of light. One of them, I'm doing them in no particular order, is called the reflecting telescope. This uses mirrors to reflect light. It uses the law of reflection, which we will talk about in a bit. The second kind is a refracting telescope. This uses a lens, actually multiple lenses, to bend or refract light. Refraction refers to bending. I'll get to that in just a bit. Let's just talk about the basic outlines of these different telescopes. A refracting telescope, I'll start with number 2 here, which is actually on the left side. A refracting telescope uses lenses. You have light entering the aperture. The aperture is the big opening on a telescope where light enters from the universe. And immediately there's a lens. That lens bends the light. In other words, refracts the light. Refract is just a word for bend. And then there's more lenses. It's more complicated than this, but basically that light is focused toward the eye, and then you can see. That's the idea. And then we have a reflector. That's the first one here. In the reflector, we have a mirror which reflects the light, just like when you look at yourself in the mirror in the morning, except these mirrors are a better quality than what we have in our homes usually. So typically there's a primary mirror, and then there is a secondary mirror, and that reflects the light to the eye. I'm going over just the very basic idea here, but it's fine for our purposes at this point. Let's very quickly go over the laws of reflection and refraction. These are the two laws that we are using to design the two different kinds of telescopes. The law of reflection says that when light hits a reflecting surface, like a mirror, it will bounce off the surface at an angle that is equal to the angle it came in with. Here is the mirror, and this is what we refer to as the normal to the surface. In this case, normal means perpendicular. It's a fancy term meaning at a 90-degree angle. So this is just a line that we draw straight out from the mirror that's at a 90-degree angle. Imagine you're looking in a mirror and a line is coming into and out of the mirror at a 90-degree angle. If a ray of light, a wave or particle of light, comes into or onto the mirror, I should say, and bounces off the mirror, the angle that that light makes with the normal, which is referred to as I, which we also call the incident angle, is equal to the angle at which the light bounces off the mirror. That is referred to as the reflected angle. So I equals R. That's all the law of reflection says. The law of refraction is a little bit more complicated. I first just wanted to show you what refraction is. Refraction is the bending of light as it moves from one medium to another. This diagram here, this picture here, which I took off the internet, but it's in the public domain, so that's okay, depicts a pen, that's the word I'm looking for, in a glass of water. As the photons of light move from the water to the glass to the air, they get bent, they get refracted, and this therefore gives rise to what looks like a bent pen, but in reality it's the light that's bent. So this is referred to as refraction. And the law of refraction is a law that governs how the light will be bent, to what extent it will be bent, and it doesn't really matter what the details are here. Okay, so this is called Snell's law, which governs exactly how light is bent. But all I really want you to know is that light bends as it goes from one medium to another, from water to air, from air to glass, from water to glass, etc. And this bending of light has to do with the different properties of materials. Some materials slow light down more than others. Remember I said that light moves at a constant speed, but that's only in vacuum. If you were to shine light through some kind of medium, some kind of molecules, such as water, diamond, glass, etc., light would slow down. And because light moves in different speeds, at different speeds, in different materials, light will bend as it goes from one medium to another. This can all be derived and explained, but it takes a bit too long. So that's all I need you to understand about the law of refraction. We use this law when we design lenses. Lenses are designed to bend light, refract light, and then we design this carefully to build telescopes. The last slide I have here is just an example of what we call a radio telescope. Not all telescopes have to be in the visible part of the spectrum. You can have a telescope that absorbs radio waves or X-rays or gamma rays. This is a particular example of a radio telescope that is designed to observe radio waves. Right? So it doesn't have to be in the visible part of the spectrum. That's all I need and want to say about this lecture. I hope that some of the properties of light have been made clear to you in this video. Thank you for watching, and I will see you in lecture 3.